All right, we're live. Hey everyone, welcome to our second build hour. This one is going to be on all things fine tuning. My name is Sarah Rabonis and I lead startup marketing here at OpenAI.
And I'm Shamal Anadkad, and I lead our Startup Solutions team here.
Now, the goal of Build Hour is really to empower you with the best practices, tools, and AI expertise to scale your company using OpenAI APIs and models. Now, based on feedback from the last Build Hour, we really heard that you wanted this to be more like a workshop series and like building live. So we're really excited to dive a little bit more into demos and some specific use cases today, and even have a customer joining us to really show how they put fine tuning into action. Now, we wanted to cover fine tuning because we hear a lot from founders how they want to really build a custom model. And we offer a few different ways that you can customize our base models, from the simplest and easiest through our fine tuning API. Our fine tuning API is going to be what we're going to cover today, but we also have more advanced techniques, which include our assisted fine tuning and custom trained models. Now, these ones require you to work directly with our OpenAI researchers and engineers to really develop a purpose-built model beyond what's possible with our fine-tuning API. Now, a lot of startups get excited about custom models. They are very exciting. Being able to build something, completely from scratch with our team is a great opportunity, but it's typically not where you should start. A lot of the time, our fine-tuning API actually covers really what you want to build and will extend itself really well to some of those custom use cases that you're building and scaling for. So let's get into our agenda. Today, we're going to start with kind of a high-level overview around fine-tuning best practices and overview. We'll talk a little bit about what fine-tuning is, when to use it versus when not to use it, and also fine-tuning versus RAG, which is a question that we hear a lot from founders. Next, we'll dive into the demo, where Shamal is going to show some examples for fine-tuning and do a great function calling walkthrough. We'll then go into some specific examples showing how you can put fine-tuning into action and include some success stories and also kind of a funny cautionary tale around how not to use fine-tuning. Then we'll pass it over to our customer Cursor, who's going to tell us a little bit about what they're building and how they've used fine-tuning for some really exciting use cases. And as always, we're going to wrap it up with a live Q&A. So in Zoom, you're going to see a Q&A button at the bottom there. Feel free to ask questions there as we're going through the presentation. We're going to have some folks from our team monitoring the Q&A. So we'll be answering questions throughout the presentation in the chat, and then Shamal will be answering them live at the end. So with that, let's get into it.
All right. Thanks, Sarah. Let's dive into it. So if you're here, you're probably already using fine-tuning in some capacity, but hopefully some of these best practices will help you get a level deeper and provide some practical insights that you can use right away. So what is fine-tuning? So fine-tuning really involves adapting the pre-trained model like GPT-4 and GPT 3.5 Turbo to specific tasks. So this process takes place by really updating the parameters of the model on the new data set. So we start with a base model like GPT-4 or 3.5 Turbo that has a general knowledge about the world, and then we try and hone their abilities through fine-tuning for a task we care about. And these training examples are a set of input prompts and expected outputs, and we expect the model will learn from these examples. And it's important to emphasize that optimizing LLMs isn't always a linear process, and most people don't start with fine-tuning. In fact, fine-tuning isn't where you should start, especially if you haven't tried other approaches to improve performance or really reach the production readiness for your task. So the diagram here is the most classic optimization flow that most of our customers end up taking when thinking about optimizing the performance of LLMs along these two different axes, which is context optimization and LLM optimization. And again, this is a hypothetical example, and the exact journey you take will depend on your use case. But most people would start with the bottom left, which is prompting, since that's the most simplest and very quick to iterate. So let's say you're working on a task, and after you realize that just prompt engineering and in-context learning does not work, then you would either try to go up the context optimization axis and try retrieval, or you go along the right on the LM optimization axis and maybe try to change the behavior of the model by fine-tuning, or you try multiple of these approaches. So essentially, you try something, evaluate, and try something else. And there's not a single answer, especially when you have several approaches to make these systems better. The most important thing here is to have reliable evaluations early on so you can measure performance against the optimization methods you try. So fine-tuning can be an involved process. So it's good to set expectations around when it's a good use case and when fine-tuning is not good at. So overall, fine-tuning is really good for emphasizing knowledge that already exists in the model, while still allowing you to customize the structure, tone, syntax, or behavior of the responses. So it's really good use case when you have a task that is really constrained and when you already have good examples and prompts for that task. Second, fine-tuning is good at following complex instructions when prompting falls short. So complex instruction often involves structured outputs, domain-specific behavior, or styles that are challenging to specify just through prompting. And this is where fine-tuning helps. And when you're fine-tuning, you don't have to include as many examples or instructions in your prompt. So this means less text and fewer tokens processed on every API call, potentially saving you cost and improving the request latency. One of the most common use cases for fine-tuning is really distilling the expertise of a large model like GPT-4 to a smaller model like 3.5 Turbo. So it's always going to be more efficient to interact with a smaller model. What it's not good at. So fine-tuning is for form and not facts, right? So it's not a good use case when you want to teach model new knowledge. This is where you should look at retrieval augmented generation or other techniques. And fine-tuning examples introducing new knowledge are learned very slowly by large language models compared to examples consistent with their existing knowledge and distributions. This is really because the models struggle to effectively acquire and retain new factual information just through the fine-tuning process alone. Also, fine-tuning won't perform well at multiple unrelated tasks that are not clearly defined. So fine-tuning works best when the tasks are related and share some underlying structure. And if the tasks are completely unrelated, it becomes difficult for the model to generalize across these tasks. One of the common questions we get here is like, when do we use RAG versus fine-tuning? So one way to think about this is RAG really augments the model's short-term memory by retrieving relevant information from external knowledge sources during inference. And fine-tuning really updates the model's weights or long-term memory by training on new task or domain. Like I mentioned, fine-tuning is for form and not facts. So first, consider if you need the model responses to be grounded to specific knowledge, then you want to start with RAG. If you want to give the model specific instructions on a well-defined constrained task, then fine-tuning can be a good use case. These, again, are additive, so it's not exclusive. For certain use cases, both fine-tuning and retrieval augmented generation will really stack up the performance on a particular task. So how do you go about actually fine-tuning a model, right? So at a high level, there are 4 steps. And as we'll see, there's a lot of complexity hidden within these steps. But you must have a data set to fine-tune on to start with, and this is often the most difficult part of fine-tuning. Some ways of getting a data set include taking an open source data set, paying humans to label the data set for you manually, or distilling the data set from a larger model, or even using some of your production samples and prompts and outputs that worked as fine-tuning examples. The training and validation data that you use for fine-tuning with OpenAI must be formatted as JSON-L documents. So for the latest models, the fine-tuning data set must be formatted in a conversational format that is used by the chat completions API. Here's one example on the left of what that looks like. So you take the set of instructions and prompts that you found worked best for the model prior to fine-tuning, and you include them in every training example. One quick tip here is to skip fine-tuning on specific assistant messages. You can add a wait key, which will disable fine-tuning on that message, allowing you to control which assistant messages are learned. And the wait key can be either 0 or 1, depending on how you want to control which assistant messages are learned. The key here is really starting with a smaller amount of high-quality fine-tuning data that is more effective than a larger amount of low-quality data. And we typically recommend starting with 50 to 100 examples, seeing how it performs, and then depending on that, scaling the number of training examples. Next, you actually perform the fine-tuning process. So the training process they'll take your data set and will gradually update the weights of the model to perform better on your task. And it's really important to understand here that the loss function used for fine-tuning is really a proxy for next token prediction and may not be super well correlated with the performance on the downstream task. And this is why really doing your own evaluations becomes really important. And one step here is really, selecting the right hyperparameters, which we'll go a bit into the next slide here. So we allow you to specify the following 3 hyperparameters, or essentially the knobs that you can tweak during the fine-tuning process. This is the number of epochs, the batch size, and learning rate multiplier. If you don't have an ML background, one analogy that really helps kind of understand these different knobs or hyperparameters is like, imagine you're training a student to solve math problems, right? So epochs is how many times you repeat the full set of problems to the student. And more epochs is more practice, but can also lead to overtraining if the student memorizes the answers. Batch size is essentially how many problems you give the student at once. Here, higher batch size is more efficient, allows the student to learn more efficiently, but it also requires more memory. And then finally, the learning rate multiplier. So this is basically how quickly the student adjusts their learning approach. So higher learning rate here means that they can learn faster, but also cause them to overshoot the answer. And this is what we call as overfitting. So after you trained your model with or without specifying the hyperparams, you want to evaluate the fine-tuned model to make sure that it actually performs the way you intend to perform. And this is beyond just going, just looking at the ML metrics that you have available post fine-tuning. For some of these tasks, like for example, if you're fine-tuning for code generation, it's often possible to execute the code and check if the outputs are really equivalent to what you expect to be. And then finally, after evaluation, you'll go ahead and deploy your fine-tuned model, which is pretty straightforward to do through the OpenAI API. And these last few steps really can form a feedback loop. So where you can monitor the performance of the model in production, sample new data, use that data to create new training data, and repeat the training, evaluation, and inference process. And doing this, you can continuously improve the model over time. Feel free to take a screenshot of this again, but here's some best practices that we've found work best when fine-tuning. So, like I mentioned, the first step is really establishing a baseline before even you graduate to fine-tune. And you might want to even break up a task into subsets with better prompts before fine-tuning further. And data sets are difficult to build, right? So starting small and investing intentionally is really, really critical. And again, the key is to optimize for really high quality examples and start with subsets of data first, evaluating performance on that small subset of data, and then scaling up the number of training examples. Once you have established a baseline, then you can go ahead and optimize for token and latency by distilling a smaller model to get similar performance for less cost and latency, or by compressing or trimming system instructions. And finally, you should always find ways to introduce automated evaluations that will really help you catch potential problems early on and improve your training data mix. Again, the key is to really improve your data before fiddling with the hyperparameters. And again, really high quality data is super, super important to get the fine-tuning results you want. All right, so let's actually dive into a demo. And before we actually do that, we're going to go through a high-level overview of what we're going to do for this task. So for the demo, we're actually going to optimize part of a drone assistant where the user interacts with the system through voice commands, which are ultimately executed by the drone via remote function calls. So the system here ensures that these voice commands for the drone are carried out in real time, and there's almost no room for errors here, right? So the design decisions here for the drone assistant really prioritize real-time processing and making sure that we can clearly either execute these commands on the actual drone or reject requests if the user provides invalid or ambiguous requests, which is, again, very important for safe drone management in various applications. Taking the first slice of this diagram, let's look at the first part of the system. So we have this query router, which is powered by the base GPT-4 model. What it does is just classifies commands, right? For example, land the drone and requests which are not commands, like how high can you fly? And the model here really interprets the transcribed text to determine the nature of the request from the user. So the requests which are not commands are handled by querying a knowledge base and responding with relevant information. So this is our typical RAG approach. An example of this is when you ask the drone, like, how high does it fly, or what are you capable of doing? And so if the input is recognized as a command, like land the drone, it routes the request to a command handling module, which is the next slice of this diagram. So for the second part of the system, we actually use GPT-4 with function calling. So we provide GPT-4 with a set of tools. Some of these are, for example, control camera or set the lighting of the drone and so on. And these commands will then execute these functions on the drone itself. So based on the command, this module will call the appropriate tool to execute the action. And if the command cannot be fulfilled by the available tool, or it's pretty ambiguous to the model, then the model should invoke a reject request function, which is also one of the functions that we provide to the model. And we let the user know that, hey, this command cannot be executed. It's pretty ambiguous, try again. And the drone controller here is really the one that interfaces with the drone hardware. So it's responsible for executing the actual drone operations based on the commands received. What we're actually going to focus on for this task is try and improve the performance of function calling here, right? So after some prompting, we realized that we're not still good at, accurately identifying the cases when the model should call the reject request function, especially in cases where the user commands are really ambiguous or confusing, and the model might confuse, one command for something else. And so this is essentially, if you think about it, a single turn task with a required tool call. So we will actually fine tune on these function calls with a very curated training data. And the training data essentially here would be, pairs of prompt to function call, function invocation messages. And the hope is that we can fine tune a smaller model, which will allow us to get more consistent and accurate function invocations that will ultimately help us improve performance of how our drone executes these commands, right? All right, so let's get into a code walkthrough. I think we can share the local screen here. Yeah, I think switch the. Sorry about that. Okay. All good? Seeing that about? Great. All right. So we're going to go through a practical example of fine-tuning with function calling. So this cookbook here is actually on our cookbook website. So feel free to open it up and follow along at home. We'll also drop a link in the chat to this notebook. So just as a reminder, we'll be fine-tuning the function calling part of the drone assistant, especially to help improve the performance around the reject request function. So again, the reject request function is pretty critical in the drone assistant, and we want to make sure that the model can actually call it accurately and reliably. So this notebook covers 3 sections. First, we start with assessing the baseline function calling performance. So we just evaluate right at the box how 3.5 turbo does on our given function, and assume that for latency and cost reasons, we cannot use GPT-4 or for a drone copilot use case. The next step is actually we generate synthetic data using GPT-4 to create a golden set of prompts and function invocations that we can use as training data. And then finally, we'll kick off a fine-tuning job and then evaluate the performance of the fine-tuned model with the base model and see how it does at some of the function invocations. So let's actually start with setting up the project here. So we're going to start instantiating the OpenAI client here. And we have few utility functions that we're going to define. The first one is pretty straightforward. This is just a get chat completions call. We're going to send the OpenAI API few set of params, including a list of functions. and we're going to return essentially the completion message along with a usage block, which we're going to use then to actually get some token counts. Next, actually, like I mentioned, really thinking about evals first is super important. So we're going to define a function here that evaluates the performance of the fine-tuned model or the base model and selecting the correct function. So this function basically takes in the model that we're evaluating, the system prompt to be used in the chat completion, a list of functions that the model can call, and then we also pass in a dictionary mapping of prompts to their expected function names. So what we're doing is actually looping through the prompts to expected tool name dictionary, and then we're finally getting the responses from the chat completions API, and we're actually aggregating the responses in data frame that shows the prompts, the actual function called, the expected function that we expect the model to have called, and see whether they match, right? So we're just trying to match the expected function to the actual function, and then printing out some statistics around the accuracy of how well the model does. And this is the system prompt that we're going to use for the drone assistant. So this is pretty straightforward prompt. You are an intelligent AI that controls a drone. Given a command or request from the user, call one of your functions to complete the request. If the request cannot be completed by your available functions, call the reject request function, and so on. And then along with the system prompt, we're going to also pass in a list of function lists. So again, this is for function calling. And let's look at the few of these functions to see how they look. So one of them is the control camera. So this will essentially, we have a description that says control the drone's camera to capture images or videos. We also pass in a few parameters. One of them is the mode and duration. So this is the duration in seconds for video capture. And then we have the mode parameter as required here. So these are the list of functions that we're going to basically give the model when we try and use function calling. One important function here is we also pass in the reject request function. So, right, the model should really use this function if the request is not possible or if the user request is ambiguous and confusing and so on. So we're going to start with some straightforward prompts, right? So let's see how function calling performs with just GPT 3.5. So we're going to call our eval function, and essentially we're passing in the system prompt here, the model that we're evaluating, list of functions, and the prompts to expected tool name. So we get this data frame back, and great. So it does pretty well on the very straightforward prompts. We get 100% accuracy, and pretty much the actual functions match what we expect the model to output. Let's level it a bit up and try some difficult requests. So we have a set of these 10 requests which are a bit more challenging, and some of these are like almost possible and seem very drone related, but the drone shouldn't actually execute this, and so we should get a lot of reject requests for some of these challenging prompts. So let's see how the model does on this. So again, we have the same eval function that's being called here, and then we're passing in the challenging prompts to expected mapping here. Great. So we're actually getting a 60% match here. So we have about 4 of these that the model incorrectly routes to a function when it should actually reject some of these requests as they are conflicting in some cases. For example, we have a user request that says change speed to -120. Of course, we cannot do this because we cannot have a negative speed for the drone, but the model actually ends up calling set drone speed. Similarly, it confuses the initiate following on social media for calling the set follow me mode function. So there's some things here that we can improve. So this is a very good use case for fine tuning. And again, we can try some prompt engineering here, but for this use case, let's actually see how fine tuning performs on, specifically getting some of the accurate responses for when the model should reject the request. So the next step is actually we're going to generate some synthetic data for fine tuning. Again, this is a lot of code, and so we're not going to go into detail, but at a high level, what we're going to do is we're going to generate every invocation for every function that we provide to the model. So essentially have full coverage of all possible invocations. Then we'll use GPT-4 to essentially come up with prompts that would call each invocation. And then finally, we'll use that prompt function invocation pair as training data. So we have 2 essential prompts here. So one is the invocation filler prompt, which takes in the function and comes up with reasonable arguments for some of the parameters that we kind of showed in the list of functions. And then we have the second prompt here, which is the command generation prompt, which again, given the function invocations, its job is to come up with a prompt that would result in those function invocations. So we're going to actually we're going to generate the synthetic data here and use GPT-4 to generate prompts that would result in those invocations. And then finally, we're also going to include some of the training data for when the functions should reject the request. So we have a reject request list here that we curated by querying GPT-4o, asking for requests that it thinks that are related to, but quite possible. And given the list of functions, it shouldn't actually execute these. So some of these are, for example, toggle night vision mode or measure wind resistance, where we don't have a corresponding function, or cases where it should really tell the user that it cannot execute this. All right. So then the next step is actually procuring the training data. So the training data actually looks something like this. So we have a list of 100 training examples. And just to zoom into one of the examples, we have the same chat conversation format with the system prompt that we showed before. A user prompt here, in this case, which is, I need the drone to go 10 feet to the right. Can you do that? And then the assistant prompt, which is essentially a single required tool call, in this case, which is, this request should result in calling the control drone movement function with the direction and distance argument. So this is one example of the training data that we have, and we have 100 of these examples, including some of those that cover the reject request function. So the next step is actually taking this training data, which is in JSON-L file, and actually, kicking off the fine-tuning process, right? So the first step here is to upload this training data to the OpenAI API. And here we have the file create function with the purpose of fine-tuning. So we're actually going to do that. And so this will actually get the training data uploaded. And the next step is pretty straightforward. We just kick off the fine-tuning job by specifying this training file ID, which we get from the response after we upload the file to the OpenAI API. And then we provide a suffix. This is just to make sure that we can easily differentiate the training job, the training job and the model that's being created after the fine-tuning. And then we kick off the fine-tuning process. So, and usually this takes either tens of minutes to hours, depending on the size of the data set and also the base model that you're trying to fine-tune. And to save us some time, before this call, I've already went ahead and fine-tuned a model on this data set. And I have the fine-tuning job ID for this here. So what we can also do is, in addition to creating the fine-tuning job and uploading the file, we can also list the existing fine-tuning jobs. We can retrieve the status of a particular job or even cancel a job. So in this case, I basically fine-tuned the model 3.5 Turbo on our training data. And this is the job ID that we get back from it. So actually check the status. So we can sort of see that the fine-tuning job has been finished at this time. And we have the model name here. So this is essentially the snapshot that we'll be using to query our fine-tuned model. One thing to note here is that after your fine-tuning job is finished, you can also see some important metrics to get a sense of how the training process has gone. So you can see kind of like the training loss, the training accuracy, the validation loss, and validation mean token accuracy. And while some of these metrics are helpful, the most important thing is, again, to have your own evaluation, right? To evaluate samples from the fine-tuned model. So this will give you the most relevant sense of model quality. So let's actually do that. So we have the fine-tuned model now. We also have the base model. So we're gonna see how the model does on the set of challenging prompts that the drone assistant should automatically reject. So again, we're gonna run this evaluation step. Again, the first step is we're evaluating the fine-tuned model. We're providing the challenging prompts. We're also evaluating the base model on the same challenging prompts, and we're passing in the function list that we have above, and then the same system prompt across both of these eval functions. So looking at the first one, so this is pretty good. So we're seeing 100% accuracy on fine-tune model with some of these challenging prompts. So all of these should be reject request, and that pretty much matches all the ones that we expected to. And comparing that with the base model, we can still see that there's about 7 out of 10. So it's about like still 70% of these requests which are incorrect and that the model should have rejected. So one thing to note here is that what we did here is we could also experiment with actually trimming down some of the parameters and description when we pass in the list of functions. So when you're fine-tuning, you have the luxury to actually trim down some of the function descriptions when you're passing in the list of functions if you really want to save on tokens or improve latency and so on. So if you see, this is the modified function list, which is where we basically remove some of the descriptions. And if we compare the average tokens used per request across both of these, we can see with the fine-tune model, we're getting about 457 average token used per request. And with the non-fine-tuned base model, we're seeing 791 average tokens used per request. So not only did we increase the accuracy and performance on function calling, but we also saved some tokens, which is a nice bonus. And now we can sort of really improve, meet the latency requirements that we need for our drone assistant use case. Great. So let's switch back to the slides. Great. So again, we successfully here, fine-tune the model to get really good at rejecting requests. And, again, because for latency reasons, we cannot use GPT-4o, we successfully saved some tokens with 3.5 turbo, improved latency. At the same time, before and after fine-tuning, we can clearly see the improvement in the accuracy of the model calling the reject request function. All right. So let's walk through a couple of success stories and then a cautionary tale around fine-tuning. And to illustrate 2 examples from real customers we work with where fine-tuning GPT-4 has led to better outcomes. On the left, we see the performance comparison for a moderation annotation task. So in this case, fine-tuning GPT-4 shows really good increase in accuracy from 0.48 to 0.75. So almost like a 56% improvement in accuracy when annotating a task for moderation. On the right, we have a customer that fine-tuned for an Icelandic grammar correction task across different models. So you can see that fine-tuning GPT-4 here results in slight improvements in 2 of these metrics that they use, the edit distance and the blue score. But it's important to note that the improvements from fine-tuning GPT-4 here over 3.5 turbo are less pronounced. So fine-tuning GPT-4 can be useful in some cases, but in some cases, performance might not be worth it. You almost want to start with fine-tuning a smaller model on a small subset of data, and then gradually increase the training examples, and then see if a more powerful, more intelligent model like GPT-4 can really help move the needle and improve the performance to meet your production readiness goal. And then one case that I think that we really want to showcase around like when fine-tuning went wrong, right? So this is a really funny example where a author of a blog post was experimenting with writing assistants, and they actually downloaded 2 years worth of Slack messages and formatted them, and then fine-tuned 3.5 turbo on those Slack messages. So they went through this long process, curated this data, and then finally they had this fine-tuned model on their Slack messages. And the first thing they ask is, write a 500-word blog post in prompt engineering. And the model replies, sure, I shall work on that this morning. And the author was really surprised. So they further asked, write it now. And the assistant said, okay. So again, the note is like fine-tuning worked well to replicate their Slack writing style, sure. But the error here is that they did not think through the data that they're providing, whether that would actually replicate the behavior they wanted out of this model. So when we typically use Slack, it's typically type first and think later. And this pretty much reflects in the message structure that the model learned here. But one learning here is that they could have validated early. So instead of starting with 140,000 Slack messages, spending hours to curate the data, fine-tuning, they could have started with maybe 100 messages and then validated early with a subset of those and see if that actually matches the style that they really wanted the model to mimic. All right, so this is, again, a fun cautionary tale. and hopefully that'll give you some insights into, when you should use fine-tuning and what are some lessons to learn early on. All right. Next, we're actually excited to have a special guest with us today, Aman Sanger, who's the co-founder of Cursor, with us to talk through some of their experience with fine-tuning. So Aman, take it away.
Thanks, Yamal. Hey guys, I'm Aman, one of the co-founders of Cursor. And Cursor is an IDE that's built for programming with AI. It is, in my opinion, the best AI-assisted coding experience, and it's powered by both very strong models and a fantastic UX. Today, I'll talk about how some of these strong models are unlocked and were unlocked by fine-tuning via OpenAI's API. Some of the core features that we offer are the ability to predict the next edit in your code base at low latency. And it's almost this superset of standard autocomplete. And I'll kind of go into detail on that very shortly. The ability to instruct and edit in some region of code, and to chat with frontier models like GPT-4o that can see your whole code base and instantly apply changes to your code. And again, in order to improve performance on seeing your whole code base, we leverage fine-tuning. So the two use cases are this kind of next edit prediction feature that I mentioned earlier, and the ability to re-rank pieces of code from all across your code base to feed into GPT-4o in order to provide more grounded results with RAG. So the first task that we used fine-tuning for was next edit prediction. Instead of the standard Copilot autocomplete, as you guys have seen, which basically will predict what comes after your cursor, we reframe the problem as predicting the next edit in a sequence of edits. So the user in their current coding session has made some number of edits in your current file, in other files. How do you predict effectively that next diff, the thing that comes next? We tried using GPT-4 prompted on this task, and it performed very, very poorly. Our hypothesis for this is that it's somewhat out of distribution of what the model can do prompted, but it is a coding task that these models are quite good at. So we kind of went to OpenAI and started fine-tuning. And in fact, after a few attempts at fine-tuning 3.5, we quickly had a model that even outperformed GPT-4. Not only that, but the latency was fantastic, where if you're running this fast enough that it has to run on every effectively keystroke, you can't use GPT-4 both for cost and latency reasons. And so in the end, we used a few different evaluation metrics. The original one was kind of an exact match on our data set, or a held out evaluation set. We found that the best kind of evaluations were head-to-head evals, meaning you look at different models and then you compare the predictions using some kind of language model grader. And the great thing here is you also have the ground truth. So you have a GPT-4 or GPT-4o that can see what model A suggested, what model B suggested, and what the ground truth was. And in general, this kind of agreed with what we felt when we deployed it as well, which is that the fine-tuned 3.5 was an improvement over GPT-4. So the next task that we used it for was re-ranking. This is kind of a standard part of a lot of sophisticated retrieval augmented generation pipelines, where the first step is embedding a corpus of documents. In our case, this would be embedding the user's full code base. Now, for the second step, after using embeddings to get the best candidate, let's say 100 possible pieces of code, we wanted to filter it down even further to feed in the best 10 to 20 blocks of code. Our first attempt at this was using 3.5, again, just prompted and having it score each block of code given the query. The problem we encountered here was that it was quite bad at kind of outputting well-calibrated or grounded answers. What this means is if you prompted it one way, it would always bias the answers towards 4 or 5. if we're kind of scoring it from 1 to 5. And then if you bias it a little bit in the other direction, it would always output scores of 1 to 2. It wouldn't really give like a valid distribution from 1 through 5. And so fine tuning kind of helped with that calibration. And the way we did this was we used for with this synthetic data pipeline that I could go into more detail about in Q&A. People have questions, and using that as the data set, we were able to train 3.5 and substantially improve performance there for retrieval in our code base. And now I'll hand it back off to Shyamala for Q&A.
All right. Thanks, Aman. That was great. Great. So we have some time for Q&A. So I'm going to start taking some questions that have been curated from the chat and then go through them. But also feel free to ask more questions through the chat, and then we can take them as we go. Great. So the first one that I have here is how many samples in a data set? So although the minimum is 10 training examples for fine-tuning, we recommend at least 50. And we've seen good performance when you start with 50 to 100 examples of well-curated, high-quality training data. Again, the focus here is really making sure that you have the data set that is very representative of your task. You have diverse samples that are representative across different tasks in case you're fine-tuning for a multitask learning. But the more the merrier, but start with 50 to 100. The second question is, what are some good heuristics for sampling or selecting data for fine-tuning? Yeah, this is a good question. So I think we've found that it's a good practice to start with what actually works best when you're prompt engineering. So before even fine-tuning, you want to start with seeing how your outputs are using prompts that work really best for that use case, and then using the same prompts for selecting, using the same prompts for actually creating the training data. Another heuristic that is really helpful in selecting data is if you have a fine-tuning task that you have with like multiple, essentially trying to like target multiple tasks, try and overfit on subsets of data first before even including examples from other tasks. So really making sure that you reach good performance on subset of data before improving kind of the data diversity is really helpful in getting a sense of how it performs. The next one is, how do you fine-tune several functions for the same model with regards to the examples in the slide? Yeah, this is a bit tricky. I think, TLDR is you have to experiment, but typically when you're not fine-tuning with function calling, the max we recommend is around 20 or so functions. Beyond that, you start to see some loss in performance. But fine-tuning actually helps you because then you can include more functions. So in some cases, you can have 60 to 100 functions that you can fine-tune. I think 100 is the max that actually I've tried. So, but the most important thing is like really making sure that you have enough examples for each of the functions that you're fine-tuning. So the diversity and quality of those functions, and making sure that you have coverage across all the invocations of the functions, especially if you have like 60 or 100 of those functions, is really important. And then making sure that the data is not like biased on few set of like functions or functionalities in that case. But yeah, typically this is where you have to experiment and have good evaluations for. Right. So the next question, besides saving tokens, how about performance? Is fine-tuning the model expected to be faster? What is the cost of fine-tuning process? Is it per token basis? I think for the pricing, I think it's live on our website. So I think we can drop a link to the exact pricing. So we kind of charge per based on like the number of training tokens, and then also on a per token basis for inference. But depending on your task, if you're distilling a larger model like GPT-4 and fine-tuning a smaller model, typically, of course, if you're trying to get the same performance, 3.5 would be a lot faster. I would say almost like 2 times as faster if you're fine-tuning 3.5 compared to base GPT-4. But again, if you're fine-tuning 3.5 and if you find opportunities to reduce or compress prompts, like the example that we showed, you can potentially save on some prompts and instructions and further improve the latency and cost. Right. So the next one is, how would you set up evals for a summarization task and data extraction task? Yeah, for summarization tasks, we actually have a great cookbook on this. I would also recommend Alon putting a link in the chat to that. But I think starting with some sort of like, you know, I think like in summarization, just the ML metrics, like just blue style type of evals won't be well correlated with human judgment. What I found is actually there's a technique called G-eval, which essentially uses, you know, a more powerful model like GPT-4 with a set of criteria that you can rank the summarization task on. So some of these criteria would involve things like coherence, the fluency of the summary, the correctness of the summary, and then essentially come up with a criteria of how a human would evaluate a summary and then ask GPT-4 to evaluate the summary, and then use that along with a weighted metric that could include some of those ML metrics like Rogue or Blue, and then basically come up with a comprehensive metric that is well correlated with human judgment. But the main thing is to basically first figure out what metrics work and which ones are well correlated with human judgment. But the GPT-4 graded evals have worked really best when I've tried it in the past. All right, let's look at the next question. How does fine-tuning compare with agentic workflows? Could you clarify the question? So I think like agentic workflows are pretty separate. Like fine-tuning is really what you're trying to do is, changing subsets of the model's parameters and get really good at the task at hand. So it's really about, supervising a set of input and output examples and making sure that the model gets really good at that particular task. While agentic workflows can and cannot involve fine-tuning, right? So for agents, you could start with a very simple sort of like assistant type of use case. And if you want that particular agent to get really good at a specific set of tasks, you can use fine-tuning for agents, but they're pretty separate. Right. Would you recommend using a special token marking of completion in the fine-tuning data set? Have you seen fine-tuned models struggle to know when to stop? Sorry, I'm not sure what this question is. Maybe we can reframe this question. I'm going to skip to the next question. What if there are errors in the generated synthetic data? What are best practices to avoid this? Yeah, great question. So for the example, we used a synthetic data just because we cannot use real like customer data for something like this. But in some cases, I think, start with eyeballing the actual data set and see how close it is to what you would expect in real world. And I think eyeballing the data set is sort of like, what you should start with before figuring out some automated ways to look at the data set. What you could do is if there are errors in the synthetic data, basically build a pipeline where you can feed those errors back into the model, create fine-tuning data that can address some of these errors, and then fine-tune the model on that data to essentially cover some of those edge cases. And by the way, with our fine-tuning API, you can also continuously fine-tune a model. So when you're fine-tuning the model, you can actually provide a snapshot of the actually fine-tuned model and then continuously fine-tune on new data. So again, the error correcting feedback loop for especially when you have synthetic data helps. But again, I think there's more things to experiment here. All right. Next question. For the drone control example, how do you prevent your model for sending commands that will cause disaster? Is it possible to exhaust those commands or use cases? Yeah, good question. I think this is where we should think about having a guardrail that is either at a step before the drone actually executes this command. So this would be a separate guardrail from fine-tuning itself, where you would sort of provide a set of ground rules of what the drone should not execute or should execute with some additional measures. And that guardrail should, could just be a prompt with some few short examples, or could be a fine-tuned model. But I think that will become very important in real life use cases. And this is a great question. And, guardrails is something that you should think about very early on. Final question. And thanks again. These are like really great questions. Can you please elaborate a little bit more on why fine-tuning is not suitable, recommended for adding new knowledge to the model? Yeah, good question. I think, like I mentioned, like fine-tuning is not good at learning new knowledge, right? Like, and there's some research that has shown that, even if fine-tuning learns new knowledge, it learns it very slowly, and it's more prone to hallucination. And this is just because when you're trying to fine-tune on essentially new data, which is very separate from the distribution that the model has seen on pre-training, it can often lead to a lot of interference between the training distributions, the fine-tuning training distribution and the pre-training distribution, and can lead to more hallucinations and could confuse the model, right? So, and you can try this actually. So for example, if you're trying to fine-tune a model to output, the scores of the last NBA or basketball season, and, you have like 100 examples that do that. And if you ask the model kind of what was the score of the basketball season in like 2020, it would mimic the style, or it should know that it should output the style in a certain way, but it wouldn't necessarily memorize the actual score. And even if it does, it would try and hallucinate, right? So again, that is to say that even if it learns new knowledge, it's very prone to hallucination due to just different training distribution. And pre-training is essentially when it learns a lot of net new knowledge, versus supervised fine-tuning is when it just, we're updating few parameters of the model, and it's not really, learning new knowledge that fast. Great. So hopefully that helps. Let me switch back to the slides here. These are great questions, by the way. So finally, feel free to take a screenshot here again. You'll have these slides available later, but I just want to end with some takeaways and recommendations, right? So, before fine-tuning, I think it's very important to make sure that you don't start with fine-tuning, right? So don't fine-tune if you don't have a clear success criteria for why you want to fine-tune. So if you don't have a clear latency, cost, or performance goal, you're better off starting with prompt engineering and then iterating your way up to fine-tuning. Second is, like, before fine-tuning, making sure that specialized tasks are really ideal for, parameter efficient fine-tuning or PEFT. And it's really hard to beat GPT-4o in sort of like broad and more general tasks. And again, like, our fine-tuning API is the most simplest and first step when you have decided that, hey, I've tried everything with prompt engineering, RAG, and other approaches. I really want to improve the performance, or have a specific goal in mind. You can sort of start with our fine-tuning API to fine-tune some of the best and the latest models, and really, find your way towards like how you want to evaluate them, and then even continuously fine-tune our models based on new training data. Or if you have new training data that really corrects some of the errors that you've seen with previous fine-tuning. So during fine-tuning, actually, some of the best practices I highly recommend kind of keeping in mind is like really making sure that you sanity check training metrics. So this is the training, validation, loss, and accuracy. You'll usually get these metrics when you're fine-tuning through the platform, or like we kind of showed in the example. You can also, after fine-tuning, retrieve the result file, which will give you a list of those metrics. And you can use some of these metrics during the fine-tuning process to essentially stop early. So if you notice along, if you're fine-tuning on 3 or 4 epochs, and if you notice that the model's really overfitting, or it's not learning that much, and you want to add more data, then you can essentially stop early. So, our fine-tuning API, you can get a new checkpoint every epoch. So you can stop after, let's say, the second epoch, evaluate the model, and then either continue the fine-tuning process, or change the data depending on how you want to proceed. Second, it's really important to prioritize smaller, high-quality data sets over large, low-quality ones, right? So this is what I mentioned before. Really important to focus on, diverse, really highly representative data. And if you have multiple people that are contributing to the fine-tuned data, making sure there is no conflicts or sort of contradictions within different training examples. And really start with fine-tuning subset of data first, with 50 to 100 examples, and then scaling up the training examples over time. The last thing is, again, like good evals and traffic samples are, could be great future fine-tuning data. So all the initial work that you do on prompt engineering evals, even if you're not fine-tuning, won't go wasted. So ultimately, good prompts can be good fine-tuning data, and good evals can also potentially help you not only validate your fine-tuned models, but potentially could be fine-tuning data early on. Great. So I think these are some takeaways and recommendations. Hopefully that helps. We also have some resources here and some background reading if you want to go and explore some of the cookbooks around fine-tuning on our cookbook website. And then we have our great fine-tuning docs. If there's any feedback or questions, please reach out again. But hope that helped and gave you some practical insight into actually how to start with fine-tuning and some of the best practices around it, along with like a real example. So we'll also be sending out these slides and recordings. So hopefully you can watch it later at your own time. Great, and thank you all.